All right, so thanks again for introducing me. My name is Jay. I'm a graduate student at MIT's mathematics department. Before I start, I just want to thank all the organizers, and it's a great opportunity, like a great honor to be offered another opportunity, continuing from last year to give a talk in this research forum. I hope the tradition continues. So today, the topic I'm going to discuss is the title says impossible figures in topology. So maybe I'll just start by introducing to you what impossible figures are, and start to build up to the main subject. So the topic of today's discussion is going to be impossible figures. So these are certain optical illusions. Some of them you might have already seen before. For example, this Penrose triangle is one of these optical illusions that is famous for being an example of impossible figure. And this is actually some example that I'm going to study in a bit more detail today, and you'll see this picture over and over over this talk. So what are impossible figures? These are certain like two-dimensional illustrations of certain three-dimensional mathematical objects, or actual like physical solid objects that look like as if the two-dimensional image is a three-dimensional, like a projection from an actual three-dimensional object. But it's impossible because the actual object that is the figure is supposed to represent cannot actually be realized physically as a solid object in our ambient three-dimensional space. So this Penrose example is one such example. Penrose triangle is one such example. And as you can see, there are some actual attempts to recover this kind of Penrose triangle in a three-dimensional space. And you can see that if you look at this sculpture, an actual sculpture from a certain perspective, it exactly looks like this 2D projection, the Penrose triangle figure that we're looking at. But indeed, this figure, although in the image it looks like as if the three edges of the triangle are actually connected at the vertices, if you try to actually realize this kind of figure in three-dimensional space, you can see that this only works in one fixed perspective. So if you look at this sculpture from this exact direction, then it recovers your Penrose triangle. But as soon as you slightly deviate from the correct perspective, you can see that the edges start to fall apart. And indeed, the actual three-dimensional figure that is supposed to be represented in this figure doesn't look like what we're expecting. So this is why the Penrose triangle is an example of an impossible figure, because the object it's supposed to represent is actually impossible in three-dimensional space. Okay, so these are kind of called optical illusions because although it's a two-dimensional figure and at first sight, it looks like a three-dimensional object, like a projection of a three-dimensional object, but as soon as you think more and use your visual intuition, you soon realize that it's actually not realizable. However, it still kind of leaves you this impression of a 3D object. It looks like as if you're looking at some 3D object, although the object itself doesn't exist. So that's why it's called an optical illusion. And Penrose triangle is like a prominent example of this. But as you can see from this list of examples that I took from Wikipedia, there's a lot of examples of this sort. So these are all kind of impossible figures. You already seen the Penrose triangle. Also, what's going to be discussed in today's talk is this Penrose staircase, which is a staircase that looks as if it's ascending at every edge, which from our intuition from just living in this three-dimensional world, we know it's impossible. And this Borromean ring is like a triply linked circles. The picture looks like as if it's realizable in 3 space, but you'll if you try to do this, you'll quickly see that you cannot do it unless your circles are made out of rubber or something. You cannot make this out of actual solid spheres. And this is also kind of important for certain branches of mathematics, but this is not the example that we'll want to focus today. So Penrose triangle is named after this mathematician Roger Penrose. He's the one who kind of promoted this. In today's discussion, we'll follow a lot his own exposition of this idea of impossible triangle, impossible figures, and how it connects to mathematics. But let me just quickly mention that this kind of impossible constructions, the idea using these figures as symbols of certain impossibility philosophically has been like a great source of artistic inspiration. And most notably, this very famous acclaimed artist, MC Escher, a lot of his works employ these kinds of impossible constructions. And you can see that the Penrose staircase appears in one of his works. And just like a lot of his great famous works, artworks, are using this kind of idea. Okay, so today I'm going to discuss or explain some of the mathematical principles behind these impossible figures. The main example I'm going to focus is this Penrose triangle. And what kind of mathematical principle is lurking behind? That's the question. And the optical illusion is demonstrating some very universal phenomenon that you will encounter over and over if you continue studying mathematics, which is global inconsistency of locally consistent data. That's just a catchphrase for now. I'll try to explain a bit more what that means as the talk proceeds. But that's the main idea that's being demonstrated by this two-dimensional, nice artistic picture, the Penrose triangle. Mathematically, the corresponding notion is called cohomology. This is just mathematical jargon for describing this notion, and really this mathematical notion of cohomology is what I'm trying to describe through this talk. I'm not going to sort of throw at you all the formal definitions and rigorous constructions that go into actually defining things like cohomology, but I'll just try to explain the basic idea behind it. So the main example for today, at least for the first part of the talk, is going to be this Penrose triangle. It's going to be an example of something called cohomology, non-zero cohomology. And in the second part of the talk, after I'm done explaining what cohomology is through this example of Penrose triangle, I'll try to briefly explain how this is relevant to certain branch of mathematics called topology, how the idea of cohomology and this kind of global inconsistency of locally consistent data can be used to study certain global geometric properties of mathematical spaces. So that's the basic outline of the talk. And maybe I'll begin by discussing the Penrose triangle in a bit more detail. Okay, so the Penrose triangle, well, it's a nice, nice, cute picture, but why is it interesting, right? So as I've already explained, it's kind of an optical illusion. It seems like it looks like some projection of an actual object, but we know from our own experience, our intuition with vision, we just know that such an object cannot be realized in 3 space. And indeed, we've seen this sculpture, which attempts to recover this, but it only works in a certain perspective. Like it only works in one direction, right? So the key is that if such an object existed, so if there was a 3-dimensional object that the Penrose triangle is depicting, then this 2-dimensional picture of the Penrose triangle is going to be a projected image of a 3-dimensional object onto our 2-dimensional screen. So what we're seeing, if the object existed, would be the object would be there and just be out there in the air in some 3-dimensional space, and we have our own 2-dimensional screen, which is in this case my iPad screen or whatever screen you're watching this talk through. And the figure we're looking at on this 2D screen is going to be a projected image. So that's the basic geometry behind this. And why is the whole figure interesting? Why is it so like inspiring artistically and mathematically? Is because that it locally looks like a projected image. So although we know that there cannot be this three-dimensional object for which the figure is a projected image of, we know that this is true locally. So what do I mean by local here? That means although this whole picture doesn't make sense in 3 dimensions, we can look at certain parts of this picture. So for example, this little partial image, the part that I'm drawing circles, maybe I'll draw actual circles here so that it doesn't disappear. So you look inside this black circle, and then this part of the triangle does look like an honest image of some honest 3-dimensional object. So that object can certainly exist in 3-dimensional space. This is also true for other parts. So say I look at this lower third of this picture, then again, the part that's inside the orange circle just looks like an honest projected image of some 3-dimensional object. Same goes for this other part as well, right? So really, locally, this picture doesn't have any problem. The figure is an honest projected image of some honest object. So locally, there's no problem. And what is interesting is that if you try to interpret the whole diagram, whole figure as a projected image, then you arrive at some contradiction. So if you look at this figure locally, at every partial part, like at every little part, this partial image, there's no inconsistency or contradiction that's happening. But if you try to look at all 3 parts at the same time, if you look at this globally, then you arrive at certain contradiction. So this is where the problem occurs, and this is why it's sort of interesting, right? So locally it makes perfect sense, but globally it suddenly doesn't make any sense. So this is an instance of this phenomenon that I was trying to describe. This is what I'm trying to say mean by global inconsistency of locally consistent data. Locally, everything is consistent, looks like a projected image, but globally, it's no longer consistent. It's not a projected image of an actual 3-dimensional object. Okay, so that's why this whole optical illusion is kind of interesting, and that's why it's also interesting mathematically, right? So let me try to elaborate a little bit more precisely about what I mean by this global inconsistency of locally consistent data. And I'm trying to define for you what cohomology is in this direction. So first, I'll try to explain in more precise terms what this locally consistent data would mean in this context. Okay, so what's our local data? So again, the figure that you're looking at on this 2-dimensional screen is going to be a projected image of some 3-dimensional object, right? So that's our basic idea. And the local data that you're associating to this partial image is the following thing. So when you look at this 2-dimensional image and you try to interpret this as a projection, then you realize that there's actually this kind of projective ambiguity. What do I mean by that? So there can be like these different 3-dimensional objects which differ in their scale, in their size, and also differ in their distance from the observer's eye, but proportionally. Then, well, these objects are called similar objects, right? And just usual 3-dimensional geometry. So if you have these kind of similar objects that differ in scale and distance proportionally from the observer's eye, then you will soon notice that their projected image on the screen in which you're drawing this figure, or in which you're observing this kind of a 2-dimensional image, they will project onto the same image. So conversely, what that means is that if you just look at the image, then there's this ambiguity. You don't know where the actual 3-dimensional object is, because there can be infinitely many choices of the actual position and the size of the object that projects onto the same image on the screen that you're looking at. So that's kind of the local data that you're going to associate to each local piece. By local piece, I mean this kind of partial image, the black and orange and blue circles that I've drawn to separate parts of the Penrose triangle. So each of those partial regions, you're going to interpret that partial region, the partial figure, as a projected image of some honest three-dimensional object. And as soon as you try to make that interpretation, you introduce this kind of extra ambiguity. You're making a choice. When you think of that as a three-dimensional object, you need to fix where the object is. Equivalently, how far it is from your eye, and equivalently how sort of big it is, because everything has to increase proportionally. So in sum, to summarize, interpreting this kind of figure locally requires, as a projection, requires this extra choice of data. And that is the local consistent data that we're associating to each local piece. And that's the locally consistent data, because if you just look at this local, like a partial image, then there's sort of, once you make the choice for one point, then other points kind of you can deduce from the geometry you're seeing, and that's consistent because the picture looks like a projection. Right? Hoping that's making sense. So that's the locally consistent data part. And now I'm trying to, now I'll try to explain to you where the global inconsistency arises. So far, what the things we have done are the following. So we start with this Penrose triangle, a nice two-dimensional figure, and we've sort of partitioned that two-dimensional figure into three pieces: the black and orange and blue circles that I drew. And the key is that each of the partial image of the Penrose triangle, if you look at it, it's a locally consistent piece. So it looks like a projected image of an actual existing object, right? So I've broken down the triangle into three pieces, and you can see that the pieces kind of overlap. You have this kind of overlapping region. So for example, this piece and this piece looks disjoint, but they have some regions that correspond to the same point in the original picture. So that's what I mean by overlaps. So the first thing we've done is to break down our triangle into three pieces. Three is kind of arbitrary. You can do this as long as things look consistent in each of your smaller pieces. And three is the one I chose. Okay, and we've chosen this local data. So we've considered, we've broken down our triangle into three pieces. And for each piece, now we are interpreting each piece as a projection of an honest object. So as I've explained, this kind of interpretation requires an extra choice. So now you've broken down the triangle into three pieces, and now you're thinking each of the piece as a image of some object. So now you have three images, three figures, locally consistent figures, and three objects corresponding to those figures. And for each object, to make sense of that in three-dimensional space, now you've chosen some distance from the eye, or the size of the object equivalently. Okay, so that much we have done so far. And now what we need to do to try to sort of patch these local information to get some sort of global interpretation, now we need to ensure certain consistency. So as I've sort of remarked briefly, we know that these pieces have certain overlaps. So you have this part, say, maybe this point of the Penrose triangle, which is just like a single point in the original figure. Maybe I'll draw that as a permanent picture. I can draw this very well, but so you have this certain point, say A, in the original picture. And now I've partitioned our figure into 3 pieces, right, like this. And these partial images have certain overlaps, which I'll denote by this green color. And now you look at some point that is in the overlap. So this point lies in the image, like a partial image of both the first piece and the second piece. And now we want to ensure certain consistency, and because we have introduced 2 different objects a priori, so before you make any corrections, the same point, this point A in the original Penrose triangle, the distance of that point from your eye may differ if you look at the first piece or the second piece, right? Because we've chosen arbitrary distances for each of the pieces. For 3 pieces, we have 3 objects, and we've made 3 choices of distances. And now if you look at this common point, then now you have 2 different choices for what the distance of this point from your eye is, corresponding to the choice you made for the first piece and the choice you made for the second piece. So if you have these kind of overlaps and you want to make sense of certain like consistency for this, then what you need to do is, as you move from this first partial image to the second partial image, you need to correct by multiplying certain scaling factor. So by that, what I mean is that the distance of this same point, if you look at this in the first chart, that's some distance. If you look at it in the second partial chart, then it's going to be another distance. And to correct this kind of difference between these 2 distances, what we're going to do is we will introduce certain multiplicative factor such that if you multiply this factor to the distance from coming from the first partial image, first object is going to equal to the distance of the second object. Okay, so we've introduced this kind of extra scaling factors, which sort of corrects the difference that we've introduced by choosing arbitrary scales for each of the 3 pieces. So hope that makes sense. And I'll denote that by that scaling factor by mi to j, where I and j are certain indices 1, 2, 3, corresponding to our 3 pieces. And if you move from chart I to chart j, this partial image I to partial image j, then the distance is going to get multiplied by this mij. And that's a positive real number. This is scaling factor, right? So now what's the key observation? The key observation is the following. So by proof by contradiction, suppose that the figure that you were looking at from the beginning, the Penrose triangle in this example, was a projection of an actual honest 3-dimensional object that exists in the 3-dimensional space. Suppose that is true. We know that it's not true, but for the sake of contradiction, suppose that it's true. Then these partial images and the partial objects that we're considering are just going to be some magnified versions of the parts of the original single object that exists in 3-dimensional space. So what that means is that we can have one consistent, globally consistent scale for all of the 3 pieces. And numerically, what that means is that we have some global reference scale in which our actual object exists. And each of these local scales that we made choices for in the part where we associated local data to each local piece, now we can think of those local scales as multiples of some one global scale. So we can now associate certain positive real numbers to each of these local scales as well, in reference to some global scale. And indeed, if you have these kind of local scales in terms of one global scale, so if you have 3 real numbers, S1, S2, S3, in which your distance to each local piece is represented by these real numbers, then the scaling factor now has this sort of easy form, which just becomes a ratio of the global scale, global local scales. So as you move from chart 1 to chart 2, or or partial object 1 to partial object 2. The scale that you're using for partial object 1 is S1, and the scale you're using for the partial object 2 is S2. So the scaling factor you need to multiply to correct the difference between those local scales is just going to be the ratio of the two. And this is all happening under the assumption that we actually have an object that exists in three-dimensional space, such that the figure represents. So that's the extra assumption we need to write expressions like this. So in particular, what this gives you algebraically is the following. So I've explained to you that as we move from one partial image to another partial image, you need to multiply by this certain positive real number, which is a scaling factor. And what happens is that if you multiply these three factors cyclically, so if you move from part one to part two, oh, did you lose my screen? Okay, I don't see my screen anymore. Okay. Yeah, is it appearing now?
Yes, we see it.
Yeah, okay. Okay, great. Yeah, so under this assumption that you have this one global object, then this cyclic product of these three scaling factors, which you need to multiply as you go from chart 1 to chart 2, chart 2 to chart 3, chart 3 to chart 1. If you take the whole cyclic product of that, if you have this expression in terms of this global scale, then the product is going to be 1. So that's under the assumption that the Penrose triangle is a projection of it on this object. Now, we were making this assumption for the sake of contradiction, so we need to make sure that it doesn't work for our Penrose triangle. And indeed, what you can see is that this is impossible. So if you try to take the cyclic product of the scaling factors, this is never going to be 1 for the Penrose triangle, because as you can see from this picture, as you move from this point to, say, this point along the triangle, along the edge of this triangle, then you can see that the points are being farther and farther. So the distance of the point on the object from your eye is increasing as you go in this direction. And that's also true for this direction. Say you have this point and this point, you compare those two and you see that this point is farther from your eye. It has to be farther from your eye if this was a projection, right? So the distance gets farther and farther as you go this direction. And this distance gets farther and farther as you go to this direction, and farther as you go in this direction. So in all of these three directions, the distance of the points on the object from your eye is increasing as you traverse this triangle. So in terms of scaling factors, that means that each of the scaling factors, as you go from this chart to this chart to this chart, the scaling factors always have to be greater than 1 because you're getting farther, right? Well, in this case, because this is a single object, the scaling factor is going to be equal to 1 here, and equal to 1 here, as you move from here to here, and here to here. But as you can see, the factor from as you move from here to here, that has to be strictly positive. So this point here has to be strictly farther than this point if you're looking at it from this direction. Okay, so that's a contradiction. For the Penrose triangle, you cannot have the cyclic product of these scaling factors to be trivial, to be equal to 1. And that's why the Penrose triangle cannot exist as a honest three-dimensional object. For which the triangle itself that we look on the screen is a projection. Okay, so that's where the contradiction is. So the mathematical jargon for this is that the scaling factors, the collection of these three scaling factors of the Penrose triangle, represent a non-zero cohomology class. In this case, the cohomology is called check cohomology. Those are just names and words, but what I'm trying to deliver to you is the fact that these kind of collection of numbers which don't multiply up to 1, that's telling you that there's something called non-zero cohomology, and that's signaling this kind of global inconsistency, the behavior of global inconsistency that's inherent in Penrose triangle. So if I just make a short summary of what we did in this example, it's the following thing. We've first decomposed our original figure, our two-dimensional figure, into 3 local pieces, in which each of the piece looks like a perfectly consistent projected image of a 3D object. And for each of the local piece, now we've associated an extra data, which is the scale of the object. How far is the local object far from the eye? So we did that for each of the 3 images, and therefore each of the 3 objects, the locally consistent objects that can exist. And for each of the overlap in the partial images, we associate a certain patching data. So we associate a certain extra data, which kind of fixes corrects the difference in the ambiguity that we've kind of arbitrarily chosen for each of the local piece. And that was introduced to ensure a certain local consistency. And the final step was the important step. We considered this cyclic product, and we were trying to ask if that product is equal to 1 or not. So that means we were asking if the patching data, these collection of 3 numbers, the scaling factors, can be globally arranged so that it's actually coming from a certain actual existing object. And if not, if that cannot happen, which is in the case of non-zero cohomology, then we have this impossible figure. So that's why the Penrose triangle is describing you this idea of non-zero cohomology. It's a visual sort of demonstration of that mathematical idea. Okay, so that was the first part of my talk. So in the remaining time, I would like to introduce how this kind of study connects to a study of geometry and topology, which are branches of mathematics where we study things like shapes and spaces and so on. So the summary of the first part of the talk was the following thing. So the impossible figures were now, to us, these are now examples of figures that represent this idea of non-zero cohomology, this non-trivial cohomology. And these are exhibiting these kind of globally inconsistent behavior that comes from locally consistent data. And the implicit fact that I was using in the very last step, implicitly, is the fact that we moved around, we turned around, ran around this full circle. We traversed the cycle in our image so that the cycle is closed up. And we use that kind of cyclic structure to consider the cyclic product of scaling factors. And so we have this kind of cycle in our picture. So indeed, this kind of non-zero cohomology, that can only happen if you have some sort of non-trivial circle inside your figure. So we started with this Penrose triangle, and we see that we have this kind of circular shape, or annular shape, if you wish, that's kind of inherent in this two-dimensional object. And this is another example, the Penrose staircase that I introduced in one of the earlier slides. You also see that the kind of impossible part of this picture is coming from this kind of cycle, right? It's coming from a certain circle. And then when I say a circle, the key is that it doesn't really have to be like this round, nice circle from our middle school geometry. The circle can really be any like closed curve. So these are not round circles, but for some sense, you can consider these as these closed curves. And that sort of brings us to this notion of topology. So we weren't considering circles as like these honest circles, but now we're just looking at closed curves and just calling them circles. And that kind of classification of shapes up to this kind of weak sense, where we do not care about like this local computation, how round the sphere is, like what the radius is, whatever. The only thing we care is this kind of global behavior, that this is a one-dimensional object that closes up. And classification up to such weak sense gets us to the realm of topology. So that's just a name for the mathematical study of shapes for spaces, only up to this kind of globally interesting behavior. So I brought this nice little picture where you compare a coffee mug and a donut. And although like these two objects look geometrically very different for our intuition, the key is that topologically, these cannot be distinguished. They're both characterized by the property that these are certain three-dimensional object that has like well-defined two-dimensional oriented boundary and with one hole. So these are two 3D objects with one hole, and that's what kind of characterizes these two. And topologically, you cannot see the difference between the mug and the donut, although geometrically they look different. Logically, it's the same because their global behavior is the same. The global behavior in this case is being captured by this notion of number of holes, basically, right? And both have one hole. Yeah. Okay. So the upshot is this kind of impossible figures, or equivalently like these non-zero cohomology, can be used to detect the existence of closed curves inside our figure. And these closed curves have to be the part that supports the kind of impossible arrangement. The impossible arrangement in the Penrose triangle happens along the full triangle. For the staircase, we see that the impossible arrangement is again happening for this kind of topological circle. So again, these are not circular, but these are certain topologically they're circles because these are just closed curves. So this is how, and the key was that this kind of non-zero cohomology cannot occur unless you kind of have this circular structure. And that's the extra bit that I'm going to explain now. So why are circles really important for the existence of these kind of non-zero cohomology or global inconsistency? The key geometric fact, kind of tautological fact, is that as we move around the circle once, we come back to the very same point, right? That's what a circle is. Like you turn a big full circle and then you come back to the same point. So what does that mean? Is that if you have a globally consistent object on the circle, then these kind of local corrections that you make, these kind of scaling factors, whatever, as you move around the circle, the corrections, they have to pile up. But as soon as you come back to the place you began, then the total contribution of those corrections have to be trivial. They have to be zero or multiplicatively, the factors have to multiply back to one. So that's the necessary condition for an object to be globally consistent, an object defined on a circle to be globally consistent. So indeed, in our Penrose triangle example, we had these three numbers, the scaling factors, which measured the corrections as we move from one partial image to another partial image. The product of those three numbers have to be one. And we were asking if that number was one or not. So that's the necessary condition for the object to be globally consistent, right? So this is called the mathematical. This is another mathematical jargon. This is called the trivial monodromy condition. Trivial means that it's stupid. So in this case, it just means that the product is one. And monodromy is just like a Latin word that means, or probably Latin, or word that just means that you make one full turn. So mono means one and dromy means like some full turn. So trivial monodromy means that when you make a full turn, then you shouldn't pick up any non-trivial change in your measurement, in your corrections. So let me just illustrate that by some explicit example. So suppose you have like this circular spiral staircase. So this is some this staircase that looks like a helix, like one strand of your DNA or something like. This is some staircase, and if you look at this staircase from above, you see that it just looks like a circle, right? The staircase would look something like this. And now suppose I want to define the following object over this circle. I want to define the function of the as the following thing. You have some person walking up the stairs like this. And at each point of your circle, I want to associate the distance of that person from the ground. So I want to define that as a global function on the circle. So at each point of this staircase, so that's going to correspond to points like this. The person is walking up the stairs, and you're measuring his altitude from the ground. You want to define that as a function on the circle. And you soon realize that this is not possible, exactly because you don't have this kind of non-trivial monodromy. So if you have a staircase, that means as you walk up, you always go up. And you start from this point on the circle, and you have some distance from the ground, and you move, walk up along the stair, and the distance from the ground is going to increase as you move this direction. It's going to increase. And if you come back to the same points, now you're in a trouble, right? Because you started at a certain distance, you made a full turn, and now you arrived at some higher distance. So if you want to define the distance as a function of your position on the circle, it's not well defined. It doesn't pass the vertical line test. You cannot associate a single value to the position. And that's exactly because you have this kind of non-trivial monodromy. As you move around the circle, you pick up some non-trivial correction when you make a full turn. Okay, so, and indeed, this kind of non-trivial monodromy for this circular staircase is exactly describing why the Penrose staircase is an impossible figure. The Penrose staircase is an optical illusion of some ideal staircase which always ascends, right, on a circle. So on this Penrose staircase, which doesn't exist, you always go up, but you come back at the same point somehow, and that's not impossible. That's not possible. So this ill-definedness of the altitude function that I just described, or this non-trivial monodromy coming from this circle, is exactly explaining why the Penrose staircase is an impossible figure. So that's sort of the mathematical content of the Penrose staircase. And now I'm going to sort of explain the following surprising thing, is that the Penrose staircase, although it tells you basically that you cannot define the altitude function as a function of position on your circle, it actually gives you, still gives you some non-trivial mathematical object, which is the following thing. The Penrose staircase can be used to define a function of velocity, your speed, but not a function of your position. So what do I mean by that? So you say you're some person walking up the Penrose staircase. Now your distance from the ground is not well defined, exactly because of this non-trivial monodromy condition. However, what you can still make sense is the following thing. Although the position is not well defined, you can still define the steepness of the staircase. So just by the virtue of this picture being locally consistent. So if you look at certain part like this, maybe some partial part of this whole picture like that, then you can still make sense of how high you're going to rise if you're given the speed that you're walking up the stairs. So I'll just say that once more. So you cannot say how high you are from the ground given your position on the staircase, because that's just not well defined. You can still define how fast you can, how high you're going to rise instantaneously, given your speed. So if you know how fast you're walking up this staircase, you know how high you're going to rise in some given time. So in this sense, the Penrose staircase gives you a function of velocity, function of speed in which you're walking up the stairs, but it doesn't give you a function of the position of you on the circle, on the staircase. So this impossible figure, this existence of this Penrose staircase, it's implying the existence of certain function of velocity that does not come from a function of position. Of course, if you have a function, if you have an altitude function, if you have something global like that, then this infinitesimal altitude is also well defined, because if you know, if you have a global notion, you can just differentiate to figure out how high you're rising given some given a fixed speed. But the Penrose staircase is telling you that on this circle, you have a function of velocity that does not come from a function of position. So this is comparable to the situation of the Penrose triangle that we had before. We had these collection of scaling factors. And we had a collection for the Penrose triangle, these three numbers, the scaling factors, they existed, but they did not come from a scaling factors of an actual object. If you had an actual object, the scaling factors can be always arranged to be 1. But for the Penrose triangle, it was impossible. But similarly here, although you cannot always find a function of position, you can still find this extra thing, which is the function of speed, function of velocity. So this is another instance of this kind of cohomology. And now it's kind of different. It's not using this kind of local patching argument, but it's using calculus. It's telling you that there's some difference between position and speed, which is if you know calculus, it's a derivative of position with respect to time, right? So using calculus, you can also give new interpretations to these kind of impossible figures. And mathematicians would call this impossible figure representing a non-zero de Rham cohomology class. So it's still some non-zero cohomology, but the approach is different because we're now using calculus here. Yeah, so maybe I'll, so now that I've explained to you sort of the two main examples that I wanted to show you today, the Penrose triangle and the Penrose staircase, maybe I'll just try to conclude by explaining you why cohomology is so universal and useful in mathematics. So cohomology is this useful notion that is kind of incarnation of this universal idea, which is locally consistent data, if you collect all of them, and may have some sort of global inconsistency. And cohomology is exactly the notion, mathematical notion that captures that kind of informal idea. And I've shown you two ways to detect kind of non-zero cohomology. One was in this check sense, where we use the Penrose triangle, we decompose that into local pieces, and we saw what happens when we try to patch them up. Or there was this calculus approach, which I didn't explain in detail because I didn't want to assume that all of you already knew calculus, but so there's this de Rham sense in which you can also detect these kind of non-zero cohomologies. And impossible figures were kind of, in both cases, they were lurking behind, or they were demonstrating this non-zero cohomology. So, and the existence of such non-zero cohomology really needs this kind of non-trivial monodromy. So for something like that to happen, you'd need these kind of interesting cycles, interesting closed curves inside your the space you're looking at. And indeed, for the impossible figures, in the two cases we saw, we had these kind of circles inside them, topological circles inside them. So in particular, that means if you can compute cohomology by whatever means, it can tell you, it can give you extra information about the space you're studying. In this case, it tells you that you have these interesting circles inside your figure. So that's why, and that's sort of one use of how cohomology can be useful in mathematics. And this kind of local patching idea is also very universal in mathematics, because say you want to study some complicated object, the way people would like to do this is to just break it down into very small pieces, which are less complicated than your original thing, and it's small enough so that you can understand something about it. And then once you learn something about each of these small pieces, now you want to assemble all of that information to get the final conclusion about the original complicated thing that you started with. And always, when you try to make this kind of assembly, when you try to patch up all of these local information, you will always encounter the possibility that there might be this extra kind of global obstructions that occur in that process. And that's going to be that's always kind of captured by cohomology, and that's why it's so universal in many approaches in mathematics. So in summary, today's talk, the outline was the following thing. So we started from impossible figures, and we've sort of seen these kind of relationships among the ideas. The first idea was cohomology, which is the mathematical notion that makes rigorous this idea of global inconsistency that may possibly arise from a collection of locally consistent data. And that kind of non-zero cohomology was detected from the non-zero monodromy. So as we traverse through as we walk around some circle inside our space, we made these kind of local corrections to our measurements that we make as we move along, and we compile all of it. We pile up all the local corrections, and we move back to the same point. And if there was some change from the original situation you started with, that meant you had non-trivial monodromy. And non-trivial monodromy was kind of the main property of having this kind of non-zero cohomology. And non-trivial monodromy was only possible because we actually had non-trivial topology of in our space. And in our impossible figures, we had these interesting circles that are lying inside them. And it is really this kind of topology. Well, it depends on the person's perspective, but for people like me, these kind of topology or the geometry of mathematical objects is what we're ultimately interested in. And in cohomology, which are some like vast mathematical generalizations of the impossible figures that you've seen today, are very useful for their study. So that was sort of the conclusion that I wanted to deliver to you. Okay, so I think that concludes today's talk. So a lot of these figures and the explanations about the check cohomology of the Penrose triangle, that comes from Penrose's original article on the cohomology of impossible figures. It uses it's almost not much harder than what we've discussed today. It also has a couple more examples that I wasn't able to cover due to time constraints. So if you're interested in learning more about these, I recommend taking a look at this reference as well. Yeah, so thank you.